everybody. This is the first video that I'm going to be making for y'all. Kind of these topics we're going to be covering while y'all are out for your AP exams. And so almost all of these are going to be kind of going through pretty important theorems from analysis and from vector calculus. And the first one that we're going to kind of start with is just the fundamental theorem for line integrals. And the reason we call it the fundamental theorem for line integrals is because it's really closely related to the fundamental theorem for calculus, which I have right here with my, we'll start drawing. So we have the fundamental theorem of calculus. And remember, it just says that we can, it pretty much kind of tells us that the integral and the derivative are kind of inverse properties. Okay, so let's just kind of jump right into it and take a look at what the inverse theorem, or the fundamental theorem for line integrals is going to look like. So, what the fundamental theorem for line integrals says is that if we have this differentiable function f, and notice it can be of 2 or 3 variables, and we can actually kind of say or n or more than that, you know, however many we want. Then if we have f as a differentiable function of some number of variables and the gradient vector is continuous, then we can evaluate that the line integral of that gradient vector by just evaluating it at the endpoints of our parameterization of C. Okay? So in other words, what that says is that all we have to really worry about if we have a gradient vector field and we're taking a line integral through it, that's what this says. So remember, delta F is a gradient vector field. And so this whole thing here, it's just the line integral through that vector field along that path C. And this tells us that this integral depends only on the endpoints of C. So notice, this is the endpoint at A. And this is the endpoint at B. And so this integral, this line integral, only depends on the endpoint. That whole path in the middle doesn't really matter at all. And so that's actually a pretty significant result when you really get down to it. That tells us A, we don't really have to worry all that much about the path between the points. We just have to worry about the point to the end. And so B, what that kind of further tells us is that we don't have to worry about the path. We absolutely don't have to worry about how the path is parameterized. All we have to worry about is the input. But we're going to kind of get into that and kind of talk through some of the implications. We're going to talk through some of these implications as we go through it. Okay? So let's kind of look at a special case. Let's look at how we can maybe prove this integral. Okay? So, or prove this theorem. Okay? So let's take a look at that. Well, what we want to do, we're going to assume that f is a function of 3 variables. Now we'll say those, we'll just call them X, Y, and Z, like we usually do. Okay? And then let's kind of pick our parameterization. So we'll say that C is the curve parameterized by some vector function R of C equals, and we'll just call it X of C, Y of C, and Z. Okay? So let's kind of take a look at what this integral is gonna look like. Okay, so we have the integral over C of the gradient vector field of F dotted with dr. Okay, so the first thing that we want to do is let's kind of just rewrite this. Looking at how we kind of saw how to rewrite D. So remember, we can rewrite dr right here. This is just equal to r prime of t times dt. And so we're going to have f, the gradient of f of r of t dotted with r prime of t dt. Okay, so what I want to do now, very briefly, is also notice, that we can actually go ahead, being that we've turned everything here, we put this in terms of t, and we've also put this in terms of t. So we can go ahead and change our bounds, and so our bounds are just going to be from A to B, because of how we parameterize our curve. And so I'm going to write out the gradient function, the gradient vector as a vector, and so we know that this is going to be the partial derivative of f with respect to x, and then the partial of f with respect to y, and then the partial of f with respect to z. And we know this tells us up here, again, that tells us it's going to be evaluated at x, y, and z, kind of based on our parameterization. But we can just write it kind of as this. Okay? And then let's also expand out what r prime of t is going to look like. So remember, we said that r of t is just this vector x of t, y of t, and z of t. So r prime of t is just going to be partial with respect to t of x, and the derivative with respect to y. I'm sorry, I said that backwards. It's going to be the derivative of x with respect to t, and then the derivative of y with respect to t, and then the derivative of z with respect to t. Okay, so we can kind of substitute that back in, and we're going to have the x dt, the y dt, and the z dt, and then we're evaluating this integral with respect. Okay, so if we take one more step, that I think that this will really kind of clean up and look pretty recognizable. Okay, when we evaluate this dot product, we're going to have kind of our first term times our first term. So that's going to be df dx times dx dt. Technically, I guess not partial, so it's just the derivative. And then we're going to have plus the second term times the second term. and then we're going to have plus the third term times the third term, which is going to be d2. And again, we're still integrating with respect to, but it's no longer a vector. It's now just a scalar because that's how we got one. Okay? So, this might be a little hard to recognize, but it's actually almost a direct application of the chain rule. Except we're kind of using the chain rule in reverse. Okay? So what I mean by that is, remember, if we have f of r of t, which equals f of x of t, y of t, z of t, then when we take the derivative with respect to t of this f of r of t, what's that? Yep, that's right. When we take the derivative, remember, we have to take the derivative of the function with respect to that function's first variable, and then multiply by the derivative of that variable with respect to our independent variable t. So in other words, we just kind of took the derivative with respect to this variable, and then took the derivative of that variable. And then we do the same thing with the second variable. So we would differentiate with respect to y. We multiply by the derivative of y with respect to t. And finally, when we do the derivative with respect to the third variable, times the t. And so that's kind of the direct chain rule. And so what we kind of have to do is look up here and observe that this is exactly this. And then what we can do, we bring this integral right down here, is we know that this is going to be equal to the integral from a to b. But again, if this is equal to this, then this is also equal to this. And so we can kind of just make this substitution and say, well, this is just going to be the integral of the derivative with respect to t of f of r of t. So that's kind of the big step. Because now, from here on out, we can actually just apply fundamental theorem of calculus from way back in the day. Because what this says is we want the derivative with respect to time, but then we're integrating with respect to time. And so we can just use the fundamental theorem and say, well, this is just going to be f of r of t, evaluated from a to b, which is going to be f of r of t minus f r. And that finishes it up. That tells us, that proves the fundamental theorem for line integrals. And so kind of the only step here is that we use, the only kind of real tricky step is we use the chain rule, and we use the fundamental theorem of calculus. Otherwise, it's pretty straight computation.